Audio Jungle. Audio Jungle.
All right. Now, so that finite wing theory. This is the chapter going on. Last class we had seen one recap. I will go to you. We have seen that starting vertex, and then we had seen bound vertex, trailing edge vertex, tip vertex, and span-wise flow also we had seen. And then horseshoe vertex we had seen, right? These are the topics already we had seen that explanation and how it will be forming. Okay, that already we have seen. Now in the finite wing theory, further we have to go for like Kelvin's theory. Kelvin's circulation theory. It's called. Then Helmholtz theory and Biout law. Okay, these are the topics today we have to see. Now check. So new topic we have here. It's called Kelvin's circulation theorem. Okay, KCD. What is the Kelvin circulation theorem? It's very simple. It explained Kelvin scientist name. So it states that the time, rate of change of circulation around a closed curve. Around a closed curve consisting, this is very important, okay, consisting of the same fluid element is 0. The time rate of change of circulation around a closed curve consisting of the same fluid element is 0. So this is the statement, but how we'll understand by the diagram? Check. We can say these are the various streamlines. These are the various streamlines. See, okay. These are the various streamline, and in this streamline, we can draw a closed curve. Okay, and that closed curve we can draw like this. See, closed curve we can say this is the closed curve. This is the closed curve, okay. And in this closed curve, we can say here that circulation is what, gamma 1, and here the circulation is what, gamma 2, right? So for this closed curve, just say this is what C2 closed curve, and this is what C1 closed curve. If you check for C1, this inside this closed curve will have a same fluid element along this curve C1 at any time T1. We can say that. Okay. Here I can write this statement also. Fluid elements along curve C1, fluid elements along curve C1 at time T1. Okay, and the same fluid element for this also, the same fluid element, okay, but at a later time t2. So same fluid element we have here for curve c1 and curve c2, but different time zone, okay, different time zone, first for t1 and after some time t2, the same fluid element it is in curve c2, c1 and c2. So the time rate of change of circulation around a closed curve consisting of same fluid elements is 0. So this meaning is what, very clear. Time rate of change of circulation. What is the mean of time rate of change of circulation? I can say time rate of change of circulation. Time rate of change of circulation. That meaning is very clear. It's a change of circulation is d gamma divided by dt. In few books it is also written like d gamma by dt. It's called time rate of change of circulation. Okay, please remember this. This is one time directly asked in exam. Okay? One time it is asked directly in examination. What is the mean of it? Its meaning is very clear, that circulation will be constant. Circulation is what? It is constant. Okay, it is constant. It is not going to change. Okay, although that time t1, t2, t3, t4, anything. Okay, any curve with c1, c2, c3, but this circulation must be constant. The condition is it should be the same fluid element. Okay, same fluid element for any closed curve, that circulation will be constant. If you check, if you write this time rate of change of circulation, then obviously you will differentiate with respect to time, and then you make it 0. This is what Kelvin's circulation theorem. This is asked in exam directly. Okay, this is asked in exam directly. This was asked. This question directly they had asked in examination. Okay, it's very simple only. Hope everyone is what understood this. Yes or no? Okay. The condition is what? This is This statement is what given for a steady incompressible fluid flow. Okay. So always remember the rate of change of circulation will be zero around any closed curve for the same fluid element. For the same fluid element. Okay. This is called Kelvin circulation theorem. This is called Kelvin circulation theorem. Right. Now next we have, it is called Helmholtz theorem. What it is called? Helmholtz theorem. This is also very important. This is one more theorem in finite wing theory. Helmholtz. Helmholtz theorem. Okay. What is this Helmholtz theorem? In fact, based on this only, this circulation theory only, I had shown you that bound vertex for the closed loop. I explained that if you are taking closed loop, then circulation will be zero. In fact, for the uniform flow also. Huh? So basically, what previous you have seen, this is Kelvin circulation theorem. So this theorem will basically help you explain the generation of circulation around an airfoil. Okay. And what is the consequence of Kelvin circulation theorem? The consequence of Kelvin's circulation theorem is a proof that a stream surface which is a vertex sheet at some instant in time remains a vertex sheet for all times. It means it is not going to change with respect to time. This is also one consequence. Okay. So better let me write here. Okay, let me write here. Consequence. Consequence. Consequence of Kelvin circulation theorem. What is the consequence? Consequence is very clear. Stream surface stream surface, okay, which is a vertex sheet which is a vertex sheet at some instant in time remains a vertex sheet for all time. This is the consequence. Okay, fine. Now we will go for the Helmholtz theorem. Very important actually. So Helmholtz theorem, here it is given the four statement. Okay. So what is the Helmholtz theorem? I must, yes, Helmholtz theorem. Okay. Now, just like a stream tube, we have a vertex tube. Okay. Just like a stream tube, we have a vertex tube. So what is the stream tube? I explained that. Suppose these are the streamlines. These are the streamlines. Suppose Okay, so if this streamline will be like this, these are the streamlines. Various streamlines. If you combine it, then you may get stream tube. That they only explained when I explained the streamline potential line. So this basically stream tube is what used to uh, go for the derivation of like continuity equation and all for steady incompressible and in rotational flow. If you go for the calculation of the mass conservation or any flow pattern if you want to check, okay, so stream tube basically used for that purpose. Similarly, we have a vortex tube. So as the word only you can understand, this is the basically vortex line. Okay, these are the vortex line, or you say vortex sheet. Vortex sheet. Okay, so if you combine this, the bundle of vortex sheet will give the vortex tube. Okay, these are the vortex sheet, and this is nothing but vortex tube. Now, another way also to represent this vortex tube is, see, this will be better. That vortex tube I had here it is drawn analogy of stream tube, but if you check this diagram, it will be better to you to understand. Okay, these are called vortex tube. Okay, all right. So here this will be the vorticity section of vortex tube. Vorticity of a section of vortex tube. So here all the like a vortex sheet will be combined, then it may create a tube, okay, which is called elemental vortex line or filament. And if you make the bundle of it, okay, so that bundle often called as a vortex tube. All right. So when vortex consists of a bundle of elemental vortex lines or filament, and if you combined all this bundle, so this bundle often called as a vortex tube, just like a stream tube only. All right. So here circulation is what given, how much, gamma. Okay. This circulation for one filament I am showing, this is gamma. Similarly for all the elements, obviously vortex will be there, circulation will be there. Okay. So basically we have a four fundamental theorem, that Helmholtz theorem, the four fundamental theorem of vortex motion in an inviscid flow. Always remember this theorem is what basically given for the inviscid flow, in irrotational flow. Okay, that's the reason here in starting only the consideration has been given. Okay, now, so what are the statement? I will write here one line so it will be very clear to you. First statement, it says a fluid particle. This is very important. Okay, the question they are asking, a fluid theory based question will be asked to you. A fluid particle in general motion, possessing all or or some of the following. What are that following? Maybe linear motion, okay, linear velocity, maybe vorticity, and distortion. What is the mean of it? The fluid particles are there, okay? In that fluid particles, general motion possessing all are some of the following. So when the fluid particles are going through the motion, then it may have a linear velocity, it may have a vorticity, or it may have a distortion. Maybe all or any one or any two. Okay, but it is very clear if fluid particles will be in motion, then this thing will happen. Generally, we know it is always like linear motion, linear velocity will get. But if it is rotational flow, vorticity also will get. Distortion means that fluid particle is what distorting. Okay, that is called distortion. Hmm? Linear motion in the sense, okay, I will show you here so it will be very clear to you. See, this is called linear motion. Linear motion. Okay. Vorticity in the sense that fluid particle is what having rotation about their center mass. Okay. Vorticity. Distortion. Suppose that fluid is what, this is the axis, this is the fluid particle. The fluid particle should be like this, but now that fluid particle is what, it is distorting like this, like this. So this is called distortion. So the point is, whenever the fluid particle is having motion, then it may possess any one of this or all or any two, linear motion as well as vorticity. Vorticity a distortion or linear velocity, that will happen. Okay, this is the one thing, that this is the first statement. It was given by the Helmholtz. Okay, now we'll go for the second statement, and it's very important. Any statement related question they can ask to you. Okay, theory question. Nowadays multiple select kind of question they are asking, so they can ask you. That's the reason I'm giving the state, I'm writing here so you remember it. Okay, what is the second statement? Second statement is what? It states that the strength of vertex, that is circulation, along the length of vertex tube is constant. Okay, this is the second statement. What is said? It states that the strength of vertex, which is nothing but circulation along the length of vertex tube, is constant. Meaning is very clear. If I say this is the strength of vertex or circulation, this must be constant. Where? Along the length of vertex tube. This is the vertex tube. Just now I had drawn the vertex tube. Suppose this is the what vertex tube. Okay. So along the length of vertex tube, this circulation must be constant. That's the mean of it. This is what? Along the length, it is not going to change. That's the mean of it. Okay. Now, what is the magnitude of it? What is the magnitude of it? We can say that if the vorticity if the vorticity is zeta, and the cross sectional area, you can say, area of vertex tube is S, then what will be the circulation? Circulation is vorticity into area, that means J into S. Okay, so this is nothing but second statement. What is the second statement? That circulation is nothing but J into S. Okay, what is the J? It is circulation by S. Okay, what it indicates? What it indicates, it is very clear that vorticity is what? Increasing when area is what? Decreasing. Yes or no? So the vorticity increases and when the area decreases. Okay, and if you say vorticity approaches to infinity, that will also be correct, but its meaning is what? That area become point area. If it is point area, then it approaches to infinity. Okay, this is very important. Based on this, the question they had asked, what is the mean of it? So the vertex line cannot end. Okay, that meaning is the vertex line cannot end in the fluid in practice. Okay, the vertex line must form a closed loop or originate or terminate in a discontinuity in the fluid such as solid body or surface of separation. Okay, so let me explain this part. So like the vertex tube is what usually, let me take this, and vertex line, this is what comment, vertex line cannot in the fluid. Okay, in practice, in practice the vertex line must form a closed loop, form a closed loop. Okay, or originate or terminate in discontinuity in the fluid such as, just write the statement, this is very special actually, such as, I will explain, don't worry, solid body or surface of separation. It's very clear point that the vertex tube cannot end up in a fluid. Okay, it can end up only at a solid surface. Okay, it can end up only at a solid surface, otherwise it will go to infinite. Okay, and you can say like it is from infinite, positive plus infinite to minus infinite. It will be continuous, it is not going to originate or it is not going to terminate. Here it is clearly mentioned, this is the one comment. Okay, comments. So you can show this by the diagram also, that the vertex tube cannot originate or it cannot terminate. Okay, so I am just showing this by the filament, vertex filament. So in this filament it is started positive infinity to negative infinity. Yes, f s increases, not increases, s decreases. Check this, if s decreases then only zeta increases, and s increases, decreases in the sense what is the minimum thing possible, that suppose this is what area. Okay, this is what area, what is the minimum possibility we have here? Minimum possibility is what, this area shrink and it is shrinking up to dot, it is shrinking up to dot. Yes or no? It is shrinking up to dot. So if it is shrinking up to dot or point, then it is called point area. So if it is decreasing, then this zeta value will be increasing, and if it is approaching towards zero, okay, that minimum is what dot possible, then it is approaches to infinite. Yes or no? So as I have mentioned here, that vertex filament or vertex tube cannot end in the fluid. In practice, the vertex line must form a closed loop. Okay, it will form a closed loop. Okay, that it cannot originate or it cannot terminate basically. Okay, so that's the reason it is said like it is spread from positive infinite to negative. This is the vertex filament. It is indicating that if somewhere in the fluid it is available, okay, then it will be going to infinite. It can stop when there is the solid surface, okay, then it can stop, otherwise it cannot stop. So another one more I will show you. This is what one solid surface I can say. Now it was started from this positive infinite, but if it is solid, so it will go and it will terminate here. Okay, that's the mean of it. Now third and fourth basically demonstrate respectively that a vortex tube consists of some particle of fluid. There is no fluid interchanges between the tube and surroundings, so it is just like a mass conservation. Okay, so let me write this also. Third and fourth statement, what it is, that vortex tube consists the same particles of fluid. There is no fluid interchange between the tube and surrounding. Okay, and fourth one, the vortex remains constant at vortex move through the fluid. So this is the third and fourth statement. So make a note of it. Vortex tube consists of, I will show by the diagrams, it will be more clear. Same particle of fluid, that means there is no fluid interchange between tube and surrounding fluid. This is the one statement. Another statement, the strength of vertex remains constant remains constant as the vertex moves through the fluid. These are the statement, third and fourth statement. I will go the diagrams, it will be more clear to you. Okay, this is the third and fourth statement. Check the diagram, you will understand easily. These are the various tubes. Okay. Here, if you go for this vertex tube, here you are taking one segment. Here the circulation is what? Gamma. And this side it is d gamma. For this, what will be the value? Value will be circulation minus decirculation. Yes or no? It's saying that the vortex tube consists of the same particle of fluid. There is no fluid interchange between tube and surrounding. It is constant. So it is just like a mass conservation. It is just like a mass conservation. Okay, suppose here the vortex is what? Gamma. This is the one tube. This is the another tube. Three tubes are there. Okay, three tubes are there. This will be what? Gamma minus gamma. This is tube 1, this is tube 2, and this is what? Tube 3. So here the circulation is what? Gamma. This side circulation is d gamma, then it will be gamma minus d gamma. It's just like a mass conservation. So that's the reason that statement it is demonstrating that vortex tube consists of the same particle of fluid. There is no fluid interchange between tube and surrounding. So if there is no fluid interchange between tube and surrounding, then what will be the uh, that circulation for the vortex tube? It will be constant. The strength of vortex remains constant. It is not going to change. Okay, vortex strength will be constant. It is not going to change. So it is like you can say it's like a mass conservation. So this is all about Helmholtz theorem. Now it is over. Now the last here theorem based things. The last one is what? Biot-Savart law. This is also very important. Okay, Biot-Savart law. Remember, whatever I am explaining here, it is the gate point of views, because the subject itself, by finite wheel theory, the chapter itself is very big, but whatever it is given in your gate syllabus, that topic only I am explaining here. Okay, Biot-Savart law. And if you do this much, that will be enough. Biot-Savart law. So like in our 12th standard physics, if you remember that electromagnetism. Okay, so this basically the original is what it comes in electromagnetism. the analogy of it, we are going to write the Biot law for the this vortex tube. Okay. Otherwise, this Biot law might you have seen for in terms of electromagnetism due to intensity of electric field in the vicinity of conductor carrying an electric current to the magnitude of the current, and it will produce that magnetic field. Okay. And strength of magnetization you can find with the help of that Biot law in 12th standard physics, if you remember. So the analogous of magnetic field strength and electric current respectively, we are going to write a vertex filament. Okay. And that electric conductor will be replaced by the vortex tube. Okay. That electric conductor will be replaced by the vortex tube, and in magnetic field it was like magnetic field strength and electric current. So here it will be replaced by the vortex filament. Okay. If you do that, then you will get Biot law for the vortex tube analysis. I mean that circulation and where is the induced velocity, you can get that. Okay. So now, as I told you, this is the analogous. Okay, the analogous of the electromagnetism. Okay. Now, in electromagnetism, what you did there, you may, because in one carrying conductor is there in electromagnetism, and it is a current carrying conductor. Because of that current passing through that conductor, you will get the magnetic field. Okay, at some point. No? So here the analogous of it, if there is the vertex tube, there is the circulation in vertex tube obviously. So because of that circulation, you will get the induced velocity somewhere at any point. So that induced velocity you are going to find. Hope you understood now what we are going to do. Try to understand what I am saying. The analogous, what you are going to do, because it's a part of the electromagnetism. So that's the reason I'm saying, if you go for the full derivation, it is totally useless, not required that. It's only the analogous you need to write. If you remember, somewhere you can check, this is the electromagnetism. I will write, then you may recall. It's very easy actually. Electromagnetism. In that, what was there? There was a current carrying conductor. This was the current carrying conductor, and in current carrying conductor, the current passing through this conductor was I. Okay, and at some point P, you may get because of this current carrying conductor. This is the conductor. Okay, I is the current, and this is the conductor here. At some point P, which is at distance R, position vector R. No? So at point P, you will get magnetic field. Because of this current passing through this conductor, you will have a magnetic field. And what was that value? If you remember, B was the magnetic field. For the small part, you are going to calculate dB. So it was mu I divided by 4 pi. Okay, and small length of the current conductor, dl is the small length of the current conductor. Okay, in vector form to write, then it is dl cross r vector. Now you can relate it. So now you can relate. So analogous you can write. Okay, analogous you can write. So basically, this Biot law in electromagnetism, it was given when there is the conductor, and through the conductor there is the current passing through that conductor, and because of this current carrying conductor, around the conductor, magnetic field will be induced, okay, at some point P, which is at distance r. Same thing you are going to do for the this vertex tube. So instead of current carrying conductor, you are going to take vertex tube. There was a current I. Now here you have a circulation, or you can say verticity. So now in the same way you can write the analogous. That's all. So I'm not going to go for the all steps for the derivation. Directly formula if I will write, then you may understand that. Okay. So now if I say this is for the electromagnetism, okay, this is for the electromagnetism. Now I am considering this is the vertex tube, okay, this is the vertex tube, and in this vertex tube, this is the vertex tube, okay, in this vertex tube, that this is the gamma, which is nothing but circulation, okay, at any distance p. Suppose this is the distance p, and at distance p, which is nothing but position vector is what r. This not distance p, p is the one point and it is at distance r. R is the position vector for this conductor, for this vertex tube, and I can take this length, which is nothing but dl. So if you write what is the induced velocity here, so that induced velocity definitely it will give the direction, okay, because it's a vector quantity. So it is upward or downward, that will be explained by the thumb rule only. But magnitude, if you say what will be what will be the magnitude of the velocity, so I can say dv at point P is equal to, just analogous of this you can write, okay, what is the mu here? This mu is basically it's a permeability, okay. It depends on the medium, what type of medium. If you remember electromagnetism, it will be very easy for you. So similarly here you can write analogous, it will be a circulation, okay, upon 4 pi, because this mu into I, you can say mu into I, instead of mu I you can write circulation. As I told you, current will be replaced by the vorticity or vertex, or circulation, vorticity or vertex strength or circulation. So I am writing in terms of circulation. Rest this part will be same, dl, which is the elemental length of this vertex tube, dl into position vector r divided by r vector. So just analogous you have taken this. So this is the electromagnetism and this is nothing but vortex tube. Okay. If you check, this was the magnetic field, induced magnetic field. Induced magnetic field. So this is what induced velocity at point P. This was current. So this is what circulation. Okay. Rest everything will be same. Okay. dl is the elemental length. Here I can say this is the elemental length for this part you are calculating. This is the elemental length. Same thing here also. This is the dl, elemental length. This is what conductor. This is what vortex tube. Vortex tube. Now I think this analogy you understood. Okay, this is called analogy. Based on this analogy, we can write the equation for with the help of this law. We can write induced velocity, because vertex tube can be anything, that anything it is possible. It is vertex tube, or you can say vertex filament. Okay, vertex filament. vertex filament. Now what I will do, so this vertex filament can be anything, like it can be from plus infinite to minus infinite, okay, or you can say there is some solid surface, so it will be started from infinite and it is end up at some solid surface or solid plane, then it will be called semi infinite. If it is going from plus infinite to minus infinite, then it will be called infinite filament or infinite vertex filament. If it is going to end up at some solid plane or solid surface, then it will be called a semi infinite filament. Yes or no? So, or suppose it is connected with some two surface, solid surface, then it will be called as a finite vertex filament. Yes or no? So we'll have a different condition. For that different condition, we need to uh, write the expression, and that will be asked in your exam. And it is very important. Actually, it is asked in exam. Okay. So now we'll write this. Okay. So what is the analogous basically? Electric current analogous is what a vertex strength. Let me write here electric current. It is nothing but analogous to vertex strength, which is nothing but circulation. Okay, and electric conductor analogous to what? Vertex filament. Okay, magnetic field. It is nothing but induced velocity. Rest everything is what same. So this is nothing but analogous. What it is called? Analogous. Yes or no? So I can take this analogy and suppose this is the vertex tube here or vertex filament. I'm just going to represent. This is the gamma. Okay, this is the vertex tube strength. Now for this we can calculate the value of induced velocity at some distance. Okay, I can say here that distance, if I will draw the diagram, one more diagram I will draw, but here this diagram you try to understand. Capital R, this perpendicular distance is small r, this angle is what? Theta. This is nothing but point P, you can say. Okay. Now if you calculate what is the induced velocity, okay, for any distance, and here that distance is nothing but a small r I'm writing. So this will be what? In with respect to this formulation, that induced velocity will be dv. It is nothing but circulation upon 4 pi r sin theta d theta. This is the one formulation. Okay, now we have the complete derivation. We want the simple one only, it's not tough. I will take that two three different case I will take. Wait. First I will take for finite vertex filament. Okay. So I will say case 1. Case 1. What is the case 1? I am going to write here. Velocity induced by finite vertex filament. Okay, for this what I will say, now this vertex filament is what? Okay, it is at some, see, this is the fundamental equation. As I told you, this is the fundamental equation. By this you can go start, and this is the fundamental equation. With the help of this you can start, but the thing is, as I told you, full derivation not required here, and I'm not going to do it, will take unnecessarily time. So I will write for the finite vertex filament diagram. I will give to you, and I will explain that part also, so it will be easy to understand. Okay, in my PDF notes I will give all the step by step derivation. It will be given in my PDF notes, so there you can understand. All right, I am considering any distance h. This is the distance h, and because it is the finite, so obviously it will be defined with some angle, because if you are saying finite, so maybe you just say this is at distance a to b. Okay, and this is nothing but point p. So this length will be, okay, if I say this angle is what? Alpha. This angle is what? Beta. All right, so definitely this angle will be what? This angle will be 180 minus beta. There should not be any doubt. Now what you will do here, as I have given this formulation, circulation upon 4 pi r sin theta d theta, that perpendicular distance r is what? Perpendicular distance. What is the perpendicular distance here? It is nothing but h. So same formula I can write here. Okay, I can say induced velocity at point p dvp. So if this you will do, then you have to integrate from what? Alpha angle. You have to integrate from alpha to 180 minus beta. Okay, circulation upon 4 pi h, just like here I have written 4 pi r, so you can write 4 pi h, perpendicular distance, sin theta into d theta. Simple, in simple only I have given. As I told you, this is the standard formula here, this one. From this again you will solve it, then this final equation will come, and from this you can start integration, and then you will get But all the steps I am not going to do. I am just explaining what is the finite vortex filament and how to get the induced velocity for the finite element. Okay, so this is nothing but Vp. If you solve this, circulation upon 4 pi h, what is the sin theta integration? It is nothing but cos theta. What is the limit? It is alpha to 180 minus theta. If you solve, what you may get, circulation upon 4 pi h, yes or no? And here it is nothing but cos alpha. You just integrate it and put the limit, so you will get further calculation. So this is the Vp. Okay, Vp is what? Induced velocity at point P. It is nothing but circulation upon 4 pi h cos alpha plus cos beta. Okay, this is very standard formula. And for the finite vortex filament we have calculated, then now we can use the assumptions semi infinite, infinite, yes or no? This is what induced velocity at point P. Why this induced velocity? Because of this circulation here, yes or no? Because, and this circulation must be along the tube or along the vertex filament. It will be constant. It is the Helmholtz theorem. So everywhere circulation will be gamma. Because of this gamma only, at this point you may have an induced velocity. Okay, use right hand thumb rule, that you hold this vortex tube and extend your thumb. Your forefinger will show the direction of the induced velocity. If I do this, then induced velocity you may get downward, yes or no? Upward, downward. So that practice, once we will solve the numerical, we will get that. It's not a big issue. But this is the Vp, which is nothing but induced velocity at point P, and this induced velocity due to this circulation here. Okay, velocity induced by a finite vortex filament, huh? And by this induced velocity because of this vortex strength. It is said vortex filament. It means it is there is circulation. So this is the, hope now this one is clear. This is the one formulation which is standard formulation. Now you can take different condition. All the different condition you can take. Okay. You say like it's a semi-infinite. You say like when the point P is opposite the end of vortex. Okay. When it is infinite, we'll do first. When it is infinite, then what will happen? So I will write case 2. What will write? Induced velocity induced velocity induced velocity by infinite vortex filament. Vortex. So first of all, you will draw the vortex filament which is infinite. I can say it is infinite in the sense it is started from plus and it is going to end up at minus. Then it is infinite. Yes or no? I can say this is the vortex filament, and at some distance which is nothing but h. Okay, h at h distance, this point is nothing but p. Here you have to calculate the induced velocity. So if you say it is infinite, then what will be the angle? Okay, it is infinite means if this distance will be infinite, okay, so it is going to infinite here, then what will be the alpha and beta? Okay, you just think, and then you may get that if it is infinite, then angle alpha and beta will be 0 0. Yes or no? It will be 0 0. You just imagine, by imagination only, because we cannot travel till infinite distance, so we can imagine that. See, you think in this way. Suppose, check, now I will explain in short and you may understand. Suppose this is the point, here you are going to calculate velocity, so this will be the angle. Now here this is the point, then this will be the angle. Now this angle is what increased. Yes or no? This angle is what increased. And if it is, you are going to a long distance, okay, if you are going to long distance, then this angle again it is going to uh, increase. So what will happen? It will be a infinite angle, but if you go for the infinite inclination, then how you will get the value? Now best example, sun or moon. You are standing anywhere, and if you check, so from your head and the position of the sun or moon, anywhere if you go, then you may not get that angle. Everywhere you may get like it is in front of you, means that for infinite distance, what is the making angle? That angle will be what? 0. It is like it is in front of you, so there is no inclination, there is no 30 degree, 40 degree, 50 degree, 60 degree, because that distance is very high. Okay, you got my point or not? So if you check, if you go very long distance like here, so if you go very long distance like this, now you will understand. If you are coming from a very long distance, suppose from here, so if you are coming from here, because this distance is what fixed, it is not going to change, so now this angle is what reduced. But if you are coming from this, so this angle will be a finite angle. Again, this angle is what reduced. Yes or no? Because this height is what fixed. For this particular height, if you are at this point, then angle will be somewhat higher angle. But if you are coming from this distance, so see, this angle is what reduced. So similarly, if you go for the infinite, so you can imagine this alpha will be 0, and at the same time, if you are going to infinite, suppose from here, then again, because this distance is what fixed, so this again, this angle also beta will be 0. Hope you understood this. That's the mean of infinite. All right. So for infinite vertex, your alpha is equal to 0 and beta is equal to 0. So what will be the VP? VP is nothing but circulation, because here we have a circulation upon 4 pi h cos alpha cos beta. What is cos 0? It is 1. So what you may get? Circulation upon 4 pi h, and here it is circulation upon 2 pi h. Yes or no? Circulation upon 2 pi h. This is the value for the infinite vertex filament. Always remember. So what is the VP? Induced velocity at point P. It is nothing but circulation upon 2 pi h. Okay. This is very important. All right. Now we'll go for case third. What is case third? I can say now semi-infinite. How to go for the semi-infinite? Means semi-infinite means one side it is infinite, but at some distance it is going to terminate. So it will have some finite angle, I can say. This side it is plus infinite, you can say, but at this point it is going to terminate. Yes or no? It is going to terminate. So this diagram will be for the semi-infinite. I can say this is what point P. This distance here it is going to terminate. So you may have this angle. Again for infinite, what will be the alpha? Because it is infinite, so alpha will be 0. So what is BP? Circulation upon this question, this type of question they are asking there. So please concentrate. Okay, it's not tough, it's very simple. If you know that formula only, you can answer. So it is circulation upon 4 pi h. What is cos alpha? Cos 0 1 plus, it is finite, so beta will be given to you. You can write. So I'm writing cos beta only, because beta can be anything, because it's a finite. It can be 30 degree, 40 degree, 50 degree, 60 degree, anything, 10 degree, 20 degree. Yes or no? This is what semi infinite. Okay, semi infinite. Now one more case I will write here. Case 4. What is the case 4? I can say when P, when the point P is opposite, is opposite the end of the vertex. So what will be the value? Check what is the mean of it. Very simple. End means C. Suppose this is the vertex filament or vertex tube. Okay, vertex will be there. So this one is what coming from infinite, and when the point P is opposite the end of the vertex, okay, I'm considering this is coming from infinite, and I'm considering one point here, okay, and this is nothing but the point P, which is just opposite the end of vertex, okay, and this distance is nothing but h, okay. This assumptions I have taken from my side, like if this will happen, then what we will do, okay. So what is this angle? This is nothing but 90 degree. Okay. What is this angle? Obviously this, I told you, if it is infinite, then this angle will be maybe alpha, then it will be 0. What will be the VP here? If the circulation they have given, so what will be the VP? It is circulation upon 4 pi h cos alpha plus cos beta. It is what circulation upon 4 pi h cos alpha is 0 1 plus cos beta means cos 90, which is 0. You may get circulation upon 4 pi h. This is what we, okay. So this Vp is nothing but this is all right. Done.